ready for the clockwise to...
The Army and Naval Research Labs are on the verge of scientific breakthroughs to improve our national defense.
Right now, satellites are the only component that I can think of that the U.S. fields that is never serviced, never touched, never even close inspected.
This force-sensitive robotic arm is changing the game to help repair satellites in space. Army scientists are making enemy detection easier and faster with supervision infrared cameras. And researchers aren't just gathering the best materials for new and better weapons, they're designing them from the atomic level up.
To really protect our soldiers and against threats we haven't even thought of yet.
Accessing mainframe. Access granted.
If you wanted to cook the perfect omelet, you'd use the best ingredients, the best eggs, milk, cheese, and whatever else you like in an omelet. But what if you're the Army, and you want the best bulletproof vest, the best electronics, the best vehicle armor, or the best munitions? Well, the usual approach is the same as in cooking. You go out and you find the best raw materials. But there's a group of scientists and engineers at the Army Research Lab who are flipping this thinking on its head. Instead of just scavenging raw materials from the environment, they're designing them, one atom at a time.
I do believe that we're going to see great improvements in terms of, even when you look at sort of conventional kinds of materials, we're going to see great improvements in their strength, in their weight, how they perform, and how we make choices for what materials to use and design them for that specific application.
We really need to develop new combat systems, as we don't have the kind of fuel resources on the battlefield that we used to have, and you want to become more efficient, and you're operating in multiple environments. You really need to change and modernize and optimize your combat systems across the board, from soldier systems to vehicle systems to flight systems to wherever you need to be.
The Program Executive Office for Command, Control, and Communications Tactical, or PEOC-3T, provides soldiers with battlefield radio and computer equipment, which has to function without fail, no matter how unforgiving the environment.
For tactical radio systems, you have to be able to operate across the entire spectrum of the environment. So, for example, in Iraq, you have extremely hot conditions most of the time, a lot of dust and wind. You switch over to Afghanistan, especially in the eastern portion of the country. You go there, very cold conditions, a lot of snow, very mountainous terrain. So the difficulty with systems that are going to be deployed with units out in the operational environment is you have to be able to cover almost all spectrums of the environment on the planet.
Here at the Army Research Laboratory, scientists and engineers are designing, building, and testing mission-critical gear that can stand up to whatever nature throws at it.
Which leads us to the Designing Materials program, a multidisciplinary approach to creating super materials from the atomic level up.
So you get 5 core elements. I've got to be able to make them, that's processing and synthesis. I got to be able to describe them, that's characterization. All right? I got to be able to interrogate them, that's advanced experimental techniques. I got to be able to model them by bridging all the scales I need to actually get the results I want.
Let's break down some of the core strategies. In modeling and simulation, scientists manipulate elements at the atomic level in growth labs like this one.
In order for us to keep that edge and to maintain battlefield superiority, we've got to be able to specifically design materials for the soldier.
One atom at a time.
One atom at a time. And that multi-scale modeling allows us to do just that.
Dr. Meredith Reed and her team grow materials one layer at a time.
What will this guy be used for in the field, or what could this be used for in the field?
Well, after we do the characterization or testing and we decide that we want to make the device, we can make it into either a laser or an LED, light emitting diode. Lots of folks have seen, some of those on their keychains. And we can use this as the light source for luminescing bioagents in the field. So we could actually use this for biodetection. Bioweapons that might release harmful particles into the air. This could be something that could be very useful to giving a soldier real-time feedback on the presence of a threat in the battlefield.
During the modeling process, researchers use bridging the scales techniques to figure out how the material's behavior on the atomic scale affects its behavior on the macro scale.
We use modeling and simulation to explore materials and try to design them on the computer, see how they're going to perform, see how to tinker with them on the computer to find that optimal material to cause them to be what we want them to be.
Dr. Betsy Rice uses supercomputing to study weapons systems at different scales.
And so we know that the energetic event occurs at the atomistic scale, but the result is manifested at the observable scale. And so we've got to properly translate the information at this very, very small scale in a way that the models that represent the visual scale capture that information and accurately depict it. And so that's what bridging the scales is. It's just simply translating information at one scale for use in a model at a higher scale.
What you're doing is designing explosives that go off when we shoot them over there, but do not go off when they get hit over on our side.
That is correct. We are trying to design materials that are very, very safe, but effective when we want them to go off. And by understanding, by using modeling and simulation to understand the controlling features of the material, we'll be able to design them for use in a safer, more effective fashion.
All without doing it in a laboratory.
That is correct.
Totally in a computer.
Yes.
Those desired results are then tested using advanced experimental techniques to study the designer material under extreme pressure.
What we're interested in is obviously when we have real armor or we have real explosions or whatever, we're interested in those really high pressures, but we can't do all this advanced experimentation in the middle of something like that. So this gives us a real exposure to a really high pressure that we could see in these other events, but in a careful lab environment we can tell much more of what's happening.
And finally, actually making the material that's been designed on the atomic level. After all, the atoms of today could end up as tomorrow's life-saving electronics, munitions, and armor.
We will be impacting soldiers' lives in the field because the materials we're looking at are things they carry with them every day to protect themselves, things they depend upon to come home safe. And we want to make their job easier, make their load lighter, reduce the load they have to carry, make their vehicles safer to really protect our soldiers and against threats we haven't even thought of yet. Our ability to design something is going to go through the roof and we're going to have a lot of real breakthroughs.
Ready for the clockwise U and keep it at Alpha 7.
That is so cool.
If you look up on a clear night, you might just see one. We know they're up there, cruising around our planet, listening, watching, gathering information. These man-made systems, these satellites, make our lives better.
We use satellites basically all over the place now. The GPS system is based on satellites, so your ability to figure out where you are on a map on your cell phone, that's based on satellites. They're used in most of our communications in one form or another. So many of your telephone calls get routed through a satellite. Almost all of your television at some point passes through a satellite. We use them to predict the weather, to figure out where hurricanes are, to figure out whether it's going to be hot or cold tomorrow, and we use them for science as well.
Satellites are also critical to the defense and security of our country.
Satellites are very important for military forces, most especially the Navy and the Marine Corps, because we operate in such remote parts of the Earth that satellites in orbit around the Earth provide the best vantage point to provide us global communications as well as sensors on orbit to monitor shipping and also to monitor weather and oceanographic conditions, and also to provide global positioning system navigation and precise timing.
But satellites have their limitations. If they break down in orbit, they can't be fixed.
We build them, we launch them, we can never get close to them. So satellite servicing would help the defense capability because right now satellites are the only component that I can think of that the U.S. fields that is never serviced, never touched, never even close inspected.
I see the box rising, indicator moving 10 turns, increasing a little bit, 4 turns.
But why is that? Why can astronauts go on spacewalks to fix the Hubble Space Telescope, but not other satellites? Well, Hubble is only about 350 miles above the surface of the Earth, and geosynchronous satellites are much higher, over 20,000 miles higher, where the protective magnetic field is non-existent.
Every time it goes from light to dark, it's very extreme temperature variations because you're outside of the atmosphere and you're in this vacuum of space. Extra radiation as well because of no protection from the atmosphere. And also there's always the danger of some type of micrometeoroid or space debris that could actually hit the spacecraft.
Yeah, your lights are down? Yeah.
And so it's a harsh environment. If we send astronauts up with today's spacesuit technology, they would use their career limit in radiation exposure in 1 hour of doing a spacewalk.
Thank you. Look really, really clean.
We're not ready to send humans there now. We may be at some point, but robotic technology is ready to go there today.
Here at the Space Robotics Lab at NRL, scientists are developing and testing robots that can fix broken satellites.
So I can see a number of types of servicing. The simplest would just be a tow truck service. Come up and dock with a satellite, help it get to where it needs to be. The next type of service I would envision would be helping with stuck deployables. Satellites are launched folded up inside a rocket. Sometimes the solar panels or the antennas or some other component fails to deploy. Robotic system could easily help that deploy. The next service I would see is we could easily, right now with today's technology, do external upgrades. We might be able to add a new thruster package or a new communications package or something that attaches to the outside of the satellite. Rocket surgery will come later.
But how do you get a rigid robot to do the subtle work of human hands?
We're focused on computer-controlled docking because there's a time delay from ground to space. Going to geosynchronous Earth orbit, it can be as much as 3 seconds once you factor in time of flight through space and all the real-world concerns. So imagine if you were driving on the Beltway and your car moved 3 seconds after you turn the steering wheel. You'd come up with a new way of operating. Well, that's what we want to do in space, but we want to have the computers able to do what computers do best and come in and do the close approach docking when we have 2 satellites flying up near each other in a relatively risky environment. Get to the point that the computers can bring the docking in autonomously and then bring in computer-assisted and human-controlled servicing so we can really get into the detailed work. Let the computers do what they do best, let the humans do what they do best.
The robot is this arm, which was developed for NRL here on Earth, where there's gravity. The arm, though, needs to function out in space, where there's no gravity. So how do we test it here? The answer? This table. What is this?
We call it the air-bearing table.
Okay.
And the reason for that is each of the mass targets has these green pucks. Those are called air bearings. They have micropores on the bottom. We feed pressurized air to them, and when we do, the entire thing floats on a very, very small cushion of air, like an upside-down air hockey table.
And so right now this weighs like what, 200 pounds?
180 pounds.
180 pounds
at the moment.
And if I try and move it, it's not going anywhere.
Right.
Right. But if you were to turn on the air.
So if I turn on the air, and we'll give it a second. So now it's floating on air. You'll notice that it hasn't moved because the table has been ground to be flat within 2 1/1000ths of an inch over its entire surface. But if we push on it.
How much force did you apply there? Not very much.
Not very much at all. I used one finger.
So this is why do you have a giant air hockey table in here?
This is how we simulate what happens when you use a robot arm to reach out and touch a satellite that's floating in space. The air-bearing table basically removes friction from the equation. The difficult part of being able to just reach out and grab a satellite that's floating in space is that even though they're very large, if we push on them the wrong way, they'll float away from us, they'll start to tumble, and they have really wide solar panels, 50 meters long in some cases. If they start to tumble, the solar panel can rotate around and hit us in the back. That's a bad day. So what you have to do instead is make the robot arm so that it goes where you tell it to go, but it also senses and responds to forces the way that a human hand does. So what we've done here is we've modified the way that we control the robot so that it can feel forces that are being exerted on it by its environment, and it responds to those forces similar to the way a human hand would. So if we reach out to grapple a satellite and it's not exactly where we thought it was, what will happen is the robot will hit the satellite, sense the forces, and instead of pushing to where we told it to go, it will stop pushing.
When I'm moving this, I'm not really moving it.
That's right.
It's just sensing where I want it to go and responding to me.
Exactly. It's moving itself.
Wow. That is so cool.
Liftoff of Space Shuttle.
We launch billion-dollar satellites into orbit 20,000 miles above the surface of our planet. And if they break down or drift away, there is nothing we can do about it. But the experts at NRL are using all their scientific and engineering know-how to create space robots that function almost autonomously. If their efforts are successful, this country will soon have its very own tow truck and repair service in space.
Clear to engage or no? Stand by. Register to his weapon. Positive.
In the dangerous arena of combat operations, what you can't see can kill you.
What's he got in his hand? That was a weapon in his hand. Roger, I think it's a weapon.
In war, the battlefield is a dangerous place. And it becomes even deadlier for what you can't see.
On the gun. Roger, got the gun. Coming down.
Not seeing the enemy concealed under camouflage or not spotting a deadly gas can get soldiers killed. The Army Research Laboratory is working on improving current technology to give U.S. warfighters supervision. To see how this supervision would work, we need to start with infrared light. Infrared light, or IR, is invisible to the naked eye. Now, every object emits IR light, you just can't see it. The hotter an object, the more IR it emits. And what makes IR unique is that it can pass through smoke, fog, and haze. To detect IR light, you need a special camera. Most of them work like this. A special lens focuses the IR light onto a detector inside the camera. The detector material absorbs the light and converts it into electrical impulses. These impulses are then sent to a signal processor that translates them into video, and then that video appears on a screen.
On the battlefield, smoke screens are used to conceal movement. Now, IR light can pass through regular smoke and fog, but there are military-grade devices out there specifically made to block IR light.
To counter against these devices, ARL scientists are making current military-grade IR cameras even more powerful enough to cut through IR-blocking smoke agents. At the heart of each camera is the detector material. The more sensitive the material, the better the IR camera. Current detector materials can only absorb about 5% of IR light. Because of this low absorption rate, more time is needed to register a clear image. At the Army Research Laboratory, Dr. K.K. Choi took a standard detector material and reconfigured its structure. By using angled sidewalls, he was able to increase the detector's efficiency from 5 to 20%, allowing more light to be absorbed. But 20% wasn't good enough.
For the consumers, the commercial product, 20% is good enough. That's what, but you don't want anybody to be better than you, detect faster than you, further away from you. You want to be the best.
Register to his weapon. Positive.
Unsatisfied, Dr. Choi spent countless hours devising a theoretical model to help him accurately predict performance. And that model would become the driving force behind the project.
In the past 25 years, in the life of this technology, actually nobody can predict what will happen. People just trial and error, based on trial and error basis. You see a phenomenon, you want to predict it, you want to explain it. That's the innate nature of a scientist. But with this modeling, now we can design something you can draw a blueprint, you can make the material, you can produce what you exactly want to make.
Dr. Choi's theoretical modeling tool was a scientific breakthrough. It allowed him to modify detectors for increased sensitivity with predictable results. Using this modeling tool, he was able to reach an efficiency of 70%. It was the high point of his career.
When I first observed the detector efficiency, that is so many times higher than what I ever seen, I become so emotional that I come into tears. Because this is really the goal of my 25 years, and it's so useful for the Army. So I think it's really, really a big satisfaction in my career.
NASA Goddard Space Flight Center created a working camera using his predictions, and they were able to confirm a 30% efficiency rating. Now, other industry partners are working on cameras with predicted efficiencies of up to 70%. With time and continued work, ARL will give the U.S. military a range of these supervision devices. Helicopter pilots would be able to fly in zero visibility. Soldiers could spot and avoid poisonous gases from a distance. Ground forces could use it for marking targets, who to shoot, who not to shoot, and where not to go. And that could prevent the tragic fratricides that occur during the fog of war.
A group of U.S. service members from Yongsan recently hit the streets of Seoul to help protect some city residents from the harsh winter weather. Petty Officer Chris Church has more.
These soldiers and their families are about to do something special.
To give out sleeping bags to the less fortunate.
The group is walking around Seoul to find people sleeping outside without much protection from the elements.
Our primary focus is to give back to the less fortunate in the community after we recognized that there was a need, and to ensure that we could be a part of keeping them warm through cold winter nights.
By the end of the night, the group will hand out 16 sleeping bags to those in need.
It's just very sad to see people that don't have as much as you have. It definitely puts a new perspective on things that we take advantage of. I was happy at the same time as well to be able to give back to people, knowing that you've done something wonderful that improves their quality of life.
The volunteers leave knowing they've made a difference, and also with a warm feeling in their own hearts.
Amazing, fantastic, self-gratifying. Wow, it was just a very phenomenal experience, and I'm glad that we all had the opportunity to be a part of it.
Petty Officer Chris Church, Seoul, Korea.
The group plans to hand out care packages to another community next month.